expect our houses and our bridges and roads to be flooded. So again, we're still looking at the hydrologic cycle. We're looking at this 1.36 billion cubic kilometers of water cycling around on the surface of Earth. And we talked about the evaporative part. We talked about the precipitation part. Now we're looking at this small amount of water that actually runs off on the surface. And I'm going to show you the amount of water on a percentage basis, the next slide, of how much of this 1.36 billion cubic kilometers is in each one of these different reservoirs. The reservoir is a subcomponent of it, so glaciers versus the ocean versus groundwater. And it's really interesting to see from a point of view of what's going to be on the next test. Certainly you don't need to memorize these numbers, but do have a feel for what are the biggest reservoirs on Earth and what are the smallest ones. What are the biggest reservoirs of water on Earth? What's the biggest one? The oceans, right? We're the water planet. 71% of the surface of Earth is covered with ocean water. So 97% of water is ocean. Anyone know the next biggest reservoir? People don't usually get this. The next biggest reservoir. So I heard someone say lakes. Yep. Excellent. Glaciers. Glaciers and shrinking, right, because of climate change. If you do the math on this, how much of water is either salty or frozen? 99 1/3, right? So most of the water on Earth is in glaciers or oceans. And look at this. Nobody ever gets this one. I bet you could have gotten it. Groundwater. A third, two-thirds rather, more or less, of the rest of the water is underground. So you see that 99.9% of all the water on Earth is either locked in a glacier or underground or in the oceans. So the other stuff, and these middle ones aren't very important for this class, but the other things that we think of as pretty important as we are terrestrial beings, freshwater lakes, saltwater lakes, soil moisture are small, 9,000ths and 8,000ths of 1% of the entire volume of water in the hydrologic cycle. And the two things we study in this class, again, those of you who had Geoscience 1, remember we talked about this for very different reasons. We talked about it because we were wondering how humans can get more water, right? How can we supply water as a resource, and how can we keep this water clean? From a disasters point of view, we are caring about the things we didn't care about last semester because we are looking at the atmosphere. We didn't care about the atmosphere, and we're looking at how we can supply water to humans. 1,000th of 1% and not easily attainable. And then now we're moving on to rivers and streams. I'll use those words interchangeably. Sometimes a stream denotes a lower order river, so streams are smaller, rivers are big, but it's appropriate to use them either way. 1,000th of 1% as well. So the two things that cause the most damage, death, destruction from a natural disasters point of view are minuscule amounts of water, 1,000th of 1% of all the water on Earth. Yet, remember that tornadoes, hurricanes, and thunderstorms kill 75% of people in this country and cause 75% of the destruction. So looking at very, very small pieces of parcels of water. So here's a picture of a river. A couple of things to notice about it. What is the land use around this river? What are these straight lines? Anyone know? So it's agriculture. So rivers are actually incredibly beneficial to us. Later in class, we're going to develop a list of reasons why we like rivers, why we try to live as close to rivers as possible. They provide a number of things for us, including obviously water, right? A river is simply water moving in motion on the landscape. So it provides us with water, provides us with transportation. It also floods periodically, and that is what provides for fertile agricultural land. It dumps the sediment that it's carrying onto the edges, onto the floodplain here, and also will bring with it nutrients that plants need to survive. So rivers are actually quite beneficial to humans, and there are a lot of really good things about them. The problem, as with all these natural disasters, is not that there are rivers that flood. The problem is that we humans move onto the floodplain and expect there not to be floods. And globally, when we look at the end of the semester, sort of recapping everything that we've talked about, and you'll read this tonight or whenever you do your reading, the most deadly natural disaster ever in the history of the world is the Yellow River floods of 1931 in China. between 3 million and 5 million people died as a result of this flooding, massive flooding. So these have the potential to kill a lot of people. Why is there such a wide range? Well, you can read about it a little bit, but the reason is twofold. One, in 1931, China wasn't keeping exact censuses, track of how many people were there. And then also, what happens if people die from drowning in the river versus die from famine that happened because the agricultural system got wiped out? So now they're starving. Or what happens when people die because they have a disease? One of the bad things that happens with river waters, it can carry diseases. So they die of dysentery because they were exposed to flood water. Should you call that death as a result of a flood? Or should you call that death as a result of a famine? Or as a result of a disease? So, depending on how you group these fatalities, this was a huge, huge, huge disaster. And there have been many bad disasters, flooding disasters. So the definition of a river, there's nothing magical about this, but you have to think about a couple parts of the definition. A river is a body of water. We're talking about the hydrologic cycle. It's in motion on the landscape, so it has to be moving. If it's not moving, it's not a river. It has a clearly defined passageway, so if it's just overland flow, then that's not river water. And it carries, obviously, water, but it also, again, carries sediment, and it carries nutrients that are vital to plant growth. So body of water in motion on the landscape has a clearly defined passageway, and it carries water, but also nutrients and sediment. So that's the definition of a river. Looking a little bit about the sort of logistics, the physics of a river. And this I'm telling you about because it's interesting. I hope you'll think in and of itself, but also this is central to our lab class on Wednesday, where we're going to see how can we predict rivers flooding. Two definitions here, the river drainage basin and drainage divide. They're simple in terms of definition. The drainage basin is the area drained by that stream or river. So you figure out on the landscape, if some rain comes into the area, is it going to make its way into this river that you're looking at or some other river? So the river drainage basin, think about it kind of like a bathtub. It's the area drained, the area that stream drains. The divide is this black line here that is the dividing line between adjacent drainage basins. So it's a high point, so you can call the drainage divide topographic high on the landscape, separates out one drainage basin from another. So these are easy definitions, but as a hydrologist, as someone who studies rivers and figuring out what's going to flood and where, these definitions will change depending on the question you ask. So for example, say I'm a hydrologist and there's which I was, there's a road going right here, and you have a client that calls up and says, oh, there's 3 houses for sale, it's a new development. Which house should I buy? I'm really worried about flooding on this drainage basin. So if there's a house up here, right here, you would be worried only about this little piece of the streams that's going past the house. And then if there's a house right here, then you'd be worried about that branch there. But if there's a house right next to it, so there's 3 houses in a row, the drainage basin for this part of the river is this whole upstream branch there. So you have to figure out what is the question you're asking. Same thing, if you want to know how much water can I take from this river, you have to figure out the drainage basin, how much water will be in this area. So there are interesting questions that you can ask of a river based on the drainage basin and drainage divide. But those are the things that we care about because that will tell you how much water's in the river. So in terms of types of rivers, we're going to just talk about one because this one is the predominant river type in the world these days. The first one that we're not going to talk about, but it's worth mentioning, is fascinating, is a straight river. Straight rivers are exactly what they sound like. They're straight. There's no bends in the river like you saw in that first picture. A straight river happens usually in, so maybe the mountains, headwaters of rivers. So the slope is very, very steep, and so the water goes straight down in this passageway. If you're ever in the mountains in New Hampshire, that's sort of the closest place you can find a straight river around here. Especially in the spring when the snow melts, you can hear this noise that sounds like bowling balls knocking together. the water's traveling really, really quickly. The faster water moves, the bigger the particle size it can carry. So people sometimes get very badly injured or even perish when they're trying to cross these streams, which look small, but the water's flowing really fast and they get sucked under by these huge, huge boulders that are getting smashed together at the riverbed. So straight river, very, very fast, high slope. The next type also we won't talk about any more than to just passing mention of it, is a braided stream. And a braided stream is exactly what it sounds like, braids in a person's hair. All of these interfingering channels that come together and come apart, these carry massive amounts of sediment. So they transport a lot of sediment. The cool thing that I always like to mention about these is that before vegetation evolved on Earth, these were the only types of rivers we had on Earth. So before we were here, obviously, as well. And the reason for that, this is a piece of knowledge that we'll do swing shift because next week we'll talk about landslides, is that vegetation, the roots of vegetation is really good at anchoring sediment and anchoring the slopes. So you can't have a river bank unless you have vegetation to anchor it and protect it against the energy of the river. So again, before we had vegetation on Earth, this is the only kind of river we had. There were all these braids, and we know that from looking down at the geologic rock record and seeing that these are the only deposits that you can find. And now we have them on Earth only in two places. One, in arid regions where there isn't much or any vegetation. So really, really dry areas. Again, from last semester, we talked about deserts, right? You had this brief, intense, less than 2 inches of precipitation per year in some cases, falls all at once, and the water just runs off. So you can have braided rivers where deserts occur, and you can also have braided rivers after the terminus of a glacier. So the glacier will come along and scrape up all the sediment and all the vegetation, and then when the water starts to, or the ice starts to melt, turn to water, you have a braided stream at the other side of the terminus of the glacier. But now these are pretty rare. And the last type is a meandering stream or meandering river. Meandering just means winding. This river's winding back and forth. And also, again, these rivers are incredibly predictable, the other end of the spectrum from earthquakes, when we're talking about disasters. You can predict, based on the flow of water in this river, a number of things, including the distance between adjacent bends, including what the sediment size is that the water's carrying, because again, water's a very, very, so it's not a good carrier, but it's a good sorter. So you can predict a lot of things just by knowing one thing about this river. How fast is it flowing? So what happens here is in picture A, as the water comes onto the page, it is going faster and faster and faster and faster. It's kind of like at that part, it's a straight river, just for the top part. And then it hits the edge of the bend, and it will translate, the water will translate its energy to the edge of the river, and it will erode. So it will scour away the outside bend of the river. That's called a cut bank because it's cutting into the sediment, even though there may be vegetation there. It's eroding it away. And in giving its energy to the outside bend of the river, it will then slow down, right? It's given its energy, so it slows down. So the inside bend of the river is the place where the water's flowing most slowly. And then it will do this same thing where it will start to go faster and faster and faster and faster until it hits another bank. So you have this velocity profile where it's fastest on the outside curve and erosion goes on. You see this erosion. And then on the inside bend, again, water, the faster it's moving, the larger the particle size it can carry. If you slow it down, it's automatically going to drop out its sediment. So you have this situation on the inside bend of the river where through time, so this is time series, you're depositing, depositing, depositing. So rivers are quite dynamic, and you can imagine if you built a house right next to a cut bank without stabilizing that bank, soon your house, or where your house used to be, would be in the middle of the river. And if you wait long enough, the place your house used to be would come out on the other side, but it would be covered by sediment. So these are very, very dynamic systems. The bends are always migrating downward, and the bends are always getting over-steepened, except for, in some cases, if you look on Google Earth at anywhere along the Mississippi River, you see a number of these really cool features called oxbow lakes. Mississippi River, again, doing swing shift here because we talked about it with hurricanes, and we'll also talk about it at the end of rivers and flooding, and seeing what's going on in that region. But what happens here, again, you have the curves migrating downstream because of this cut bank and point bar, and eventually you get it so over-steepened. So we talked about this also when we talked about the jet stream, which is essentially like a wind river, that you have adjacent cut banks. There's the outside bend, and then there's another outside bend, and those will scour together and punch through as it did here, and you have a new path that is straight again, and you've isolated a bend of the river, which is called an oxbow lake. Anyone from Western Mass maybe knows the Oxbow Marina, which is in the Holyoke region. It's a great place to boat and swim and fish because you have this quiet, protected water environment. You don't have raging currents of the river water, and so it's a good place to have a marina. Boats are safe, and then you dig a canal out and you go boating on the river. So not to make too much of that, but you can see the point here is that rivers are incredibly dynamic. They are moving all the time, these bends going back and forth, back and forth. Here's a picture of a meandering stream. This is the Grand Canyon region. And again, you can see this cut banks are adjacent. So what will happen pretty soon, and I'm not giving you a time because I don't know, the reason for that is because how soon it will be depends on how fast the water's flowing, how much energy it has, and maybe a dry period and it won't do much, or maybe then a wet period and it will really carve through. And then also the geology. Is it the structurally sound crystalline rock that's very difficult to erode, or is it nice weak piles of sand or sandstone, which is the case here? So the material that's there will also show will translate into how quickly this happens. But eventually the water will come on that side, cut right through here, and go off, and you'll have isolated these two bends of the river. So that's that. So the point here, again, is that these rivers are incredibly predictable. And with knowing a couple of things, here's where we're going to get quantitative with rivers, but don't worry at all. What we're doing is adding, subtracting, and multiplying and dividing. 4 things, very simple numbers, and these are incredibly powerful predictive tools. So looking at this, hydrologists can tell, people who study rivers can tell a lot of things by knowing 1 or 2 parameters of a river. So these are just relationships, and these should be pretty intuitive to you, right? It should make sense. You might also almost be thinking this is too elementary for this class, but I'm putting it up because this is how we're going to fight flooding. By knowing these relationships and figuring out how can we pass more water through a river, which will lower flooding. And so these are the parameters with regards to flooding. We know that the wider a river is, the greater the discharge. And I'll define that term in a minute, but discharge is essentially the volume of water that's moving through the river per unit time. So if you could take a cutaway of a river, take a collection vessel, turn on your stopwatch, grab how much water in a minute, stop your stopwatch and see, okay, there were 400 gallons per minute. So it's a measure of the volume of water that's flowing, that's moving per unit time. And this should make sense to you. The wider the river, the more water it can carry. The same thing with depth. The deeper the water, the more water it can carry. The higher the velocity, right? Think about your faucet, turning your faucet on just a little, and there's a trickle, and then turning it on full blast. The faster the water flowing in the river, the greater the overall discharge there will be. And then something that we won't say too much about in the interest of time, but the faster the velocity, also the particle size that can be carried. If you're looking at these slides online, I put something called a Holstrom diagram that shows erosion, deposition, and suspension. So I decided just now to take that out. But it's an interesting diagram if you're sort of interested from a personal point of view that shows the speed of the water and how big the particle size is that can be carried. So this is the situation that you had these integral relationships, and you can also plot them. This is just a kind of unfancy plot to show you the situation that, again, each green dot is an individual river. I have nothing in mind. I just want to show you this graphically. The individual river discharge, we measure it in cubic feet per second. So you can do feet cubed per second, or you can do CFS. Smaller rivers will have lower depths, will have shorter widths, and will not flow as fast. And so they will plot down there. And then as you get the rivers deeper, wider, and faster, you'll have greater discharge. Pretty linear relationship. So again, those dots are just intended to show a linear relationship. And again, this is a powerful thing that we're going to use when we talk about flooding. So discharge, focusing in on this question for a minute of discharge. Discharge is labeled Q, and I'm just going to develop it for those of you. I know you guys are amazing students and you're not math phobic, but just in case there's someone in here that says, oh no, math, I'll just sort of develop it a little bit slowly. Stream flow equation, this is called the hydrologic equation. It's the most powerful equation in all of hydrology, and hydrology is mostly math. Pick up a hydrology text, you'll see just equation after equation after equation that seeks to quantify many things about rivers. This is by far the most powerful and important equation, and luckily it's incredibly simple. All you're doing is multiplying two numbers together. So showing you it without units, right, so it should mean nothing to you now, so that you can see at its heart, it's very, very simple. And the way that you would say this is that the discharge, that volume of water that's carried per unit time, is simply equal to the area that the water has in which to flow, so width by depth, or you figure out the channel, and I'll show you a picture of that next, how much area is there, multiplied by the velocity, which you should have an intuitive feel for, right? Driving in a car, you have velocity, miles per hour, feet per second, whatever units you want to use. So you're just multiplying two numbers together to figure out this very, very important number, which is discharge. Discharge is the volume of water. That will tell you if you're going to have a flood or not, and that will tell you how big the flood is going to be. So these are simply adding units to it. Don't freak out too much about this. Here is the cross-section of a river, and this shows you there's a bit of a rolling nature, but again, you have the speed going faster and faster. There's the cut bank, right, where it's deepest, and there's an erosive situation here. Here's the point bar where you can see sediment has been deposited, deposited, deposited. The discharge, what we're looking at, how much water is flowing in this river, is simply, again, if you could cut away the river, take a collection vessel, stick it under here, start your stopwatch, collect water for a minute or a second or some period of time, pull it away, and then measure that. So again, the example, 400 gallons per minute. Just figuring out how much water per unit time. And that's equal to the velocity, which is the speed, and then the cross-sectional area. So in the case of cross-sectional area, if you're a hydrologist and you're really doing this because you're getting paid by a client, what you would do is figure out something called the wetted perimeter. Wetted doesn't have anything to do with water. It's the area here. So you figure out the height of the stream, and then you figure out what this curve is here. For our purposes, and really when you're just doing order of magnitude calculations, which is all we seek to accomplish in a disasters and a planning point of view, you can just simplify this by saying the depth multiplied by the width, right? So approximate it as a rectangle. How deep, how wide, and how fast it's flowing. So that is the cross-sectional area. So notice the units here. The units are going to, some of them cancel out. So you have the cross-sectional river area, feet cubed. You're multiplying it by the velocity, feet squared. So feet squared plus feet is multiplied by feet is feet cubed. And then on the denominator, you have seconds. So if I ask you this question, and I will ask you a simple question like this on the quiz, a river is flowing at 2 feet per second. It's 3 feet wide and 2 feet deep. What is the discharge? Two feet per second. It's 3 feet wide and 2 feet deep. What is the area? Let's first do that. What's the cross-sectional area? 6 square feet, right. So 6 square feet, how fast is it flowing? 2. So what is the number? 12 what? Excellent. 12 cubic feet per second. So very simple, very, very simple math. It is going to be important on Wednesday, and again, it will show up on the quiz. So discharge, very simple calculation, and it is profoundly important in many, many ways across hydrology, but with regards to disasters, it's important because it will tell you whether or not you're going to have a flood. What is a flood? Well, a flood is defined as when the river water overflows its bank. So sometimes we call this the stage, the height of water in the river. So when the water in the river stage can no longer be constrained by the banks, it will flow over laterally, and that's a flood. We need to know this from a land use planning point of view. How close can we get to this river to optimize on the good without getting destroyed by the bad? The way that we show this graphically is by looking at a hydrograph. Hydrograph is exactly what it sounds like. Hydro, water, graph. It's a graph of water. So what we're looking at here is on the x-axis time, the y-axis is discharge. So you have a precipitation event at time equals to 0. Rain falls. So now you're looking at either the discharge, the volume of water per unit time, or you could also, with the hydrograph, just put the stage. Standing there looking at how high the water goes. Have a staff gauge right in the middle of the river and watch how high the river goes. So rainfall event at time equals to 0. The level of water in the river rises and then falls after the precipitation event is over. So that's a generalized hydrograph, but let's look at some more specific, although still general hydrographs. These change all the time. Rivers flood, that's what they do. There's always a fluctuation in the river water. So they change depending on a couple of things, mostly infiltration. I'll define infiltration in a minute. But it's essentially water going into the ground and being part of groundwater. We like that because the more water goes into the ground, the less water's in the river to flood. So we'll call this forested New Hampshire here, pretty flat. You have a rainfall event come into the area. The water's hitting the trees. This is a natural situation. So the water will hit the trees and it will drip down through the canopy, and then it will drip down. It's called stem flow, the trunk of the tree, and then it spreads out on the grass, and gravity will pull it through the unsaturated zone very slowly, and then it will get into the groundwater. But this will sort of keep water in that region. So only a little bit of it makes its way over the grass into the river, or over the trees into the river. So here again, we have rainfall event. You see 0 to 20% of that total rainfall made its way into the river. So here's the hydrograph. And if randomly we'll say the second tick, the second horizontal bar, is the maximum amount that that river can hold, this was not a flood. The water just rose up in the bank slowly and then receded slowly. So there was no flood. You can't tell if this is a flood looking at the hydrograph until you know bank full discharge, how much water the river can possibly carry. So now let's go to Boston with the same rainfall event, same volume of water, going into a river of the same size. This is kind of interesting because Boston, the Charles River around here is actually essentially a scoured out man-made-ish channel. So in Boston, the situation is very different because the same rainfall is falling, but now we've paved everything. And we have pitched parking lots because we don't want water to build up on the parking lot. So the rain falls, and you see of that same volume of water, most all of it goes into the river. And not only does it go into the river, because again, we've pitched things, we don't want water to be standing around on our parking lots and roads, it goes fast over the pavement. And for the same dynamic of the river, same width and depth, if this is the flood height, you see that not only was there a huge flood, more than double or almost double what the river can hold, but also it came really early. So you see that the peak in the forested area was the second tick. The peak here came before the first tick. It's called flash flooding. Rivers are dangerous in cities. Los Angeles, very, very big problem with flooding. You can read all about, I don't think it's in the book, but about the problem with flooding in Los Angeles. They actually had an extreme approach to flood control. They paved their rivers. They paved them because now water, and they made them straight, so water can go flying through the rivers. So it kind of lessened the flood, but it was flooding, but it was met with really mixed success here. So flash flooding, very big problem in urban areas. So just focusing for 1 second on this question of infiltration. Infiltration is anything that doesn't go into the flood. It's the stuff that travels through the over the ground rather, and into the ground rather, becoming part of groundwater, so it's not part of the river water. So the things that control this are really 5 main things. I don't know if I put the most important thing on here. No, I didn't. Let's see. Did I put the most important thing up here? Yes, I did. Okay, good. Okay. Degree of urbanization you saw in the previous slide. The more we pave things, and this will be important on Wednesday, basin changes. What if you have a forested region and then people start to come into the area and start paving things? What can you expect with regards to flooding on a river? So the degree of urbanization, how much pavement, how many buildings, will control whether there's more or less infiltration. You want natural, forested, or grassy soils, and you have a lot of infiltration. Also, antecedent soil moisture. Ante means before. So how much water was there before? We know from tsunami that water is not expandable or compressible the way that air is, right? So if you have a lot of rain, a lot of rain, a lot of rain, and a lot of infiltration is going on, and the groundwater is going up, 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 and then becomes essentially coincident with the land surface, if you have a rainfall event, none of that water is going to infiltrate because there's no space for it. This is a problem in New Orleans. The land surface and groundwater are at the same level. So we have this antecedent soil moisture. That is how much water was there before. You don't want a lot of water there before because then there's a lot of space for the water to occupy. Temperature. So if it's really, really hot, you'll have evaporation, which is good. It's not infiltrating, but it's also not becoming part of the river water. But at other extreme is not good. Very, very cold weather. So the ground is frozen. It will behave like pavement. So you can go up to that nice situation in New Hampshire with the river, with the forest and the grass. But if the ground is frozen, it will behave just like downtown Boston. So extremes of temperature can influence infiltration. Also the type of soil. If you have nice open sandy soil, it will foster infiltration. Water will go into the subsurface. That should make sense. There's a lot of space between the grains. But if you have, again, we're talking about New Hampshire, the granite state. If you have granite or even clay, something that is very, very, very difficult to have water get into, then it will run off. It will behave like pavement. And the last thing is slope. That should make sense to you if I don't have my tea here. But if I had my tea and poured my tea onto this, we'll do this again with keys when we talk about landslides, if you can believe it. Poured some tea onto this table and it's flat. Where's it going to go? Nowhere, right? It stays right there. So flat surfaces favor infiltration. The water will sit there and slowly or quickly sink in. But if I tip this table way up and pour tea on it, what's going to happen? Yeah, it'll run down, run off. So the greater the slope, the more water will make its way into the river. The flatter the area, the more it will infiltrate. So that's good because you don't have flooding. So high slopes. Again, next week we're talking about landslides. So we'll put these all together. Rivers, flooding, landslides, and slopes. So problems associated with rivers. I'm just going to put these all out as sort of summary. Let's see. Yeah, okay. Some of the problems associated with, if you're writing these down, leave some space because we'll talk about them all. Some are pretty obvious, right? Fatigue, you're swimming through floodwater trying to save your family, trying to rescue your possessions, depression when you realize your house is destroyed, injury. In much the same way that flying debris can injure people in a hurricane, floodwaters can carry a lot of debris and you could be hit by floodwater. Disease. River water that is flooding is disgusting. It's filled with diseases. Again, with these linkages, we'll talk about pandemics and we'll talk about the role of floods in creating outbreaks of infectious diseases. This was interesting. A couple of years ago, I was teaching this class, and afterwards, this kid who had transferred from Connecticut College was talking about how he rowed crew for the Connecticut College crew team. He's like, oh, you want to hear a gross story? I said, always. So he said, so I was rowing crew for the crew team, and the Connecticut River was going to flood. And so the coach told us to go down to the boathouse and get the skulls and bring them up to the gym because we didn't want the boats to be knocking together. Obviously, boats can get wet, not a big deal, but they don't want it to be damaged. So the crew team all went down and they waded through the floodwater and they got the skulls and they brought them up to the gym. And that night, every single one of them was hospitalized with either bacterial or viral illness. They were very, very ill. Turns out that there was a wastewater treatment plant directly up gradient from the Connecticut College boathouse, and it was overflowing raw human sewage into this water. So gross, right? So they were all okay, but they spent a night in the hospital and were very, very ill as a result of this. Flood waters are very, very rife with disease. Disease gets carried on these waters. Again, we'll talk about that when we talk about pandemics. Pests after floods, you have outbreaks or increased population of things like mosquitoes, rats, etc. They will increase. Pollution, as with tsunami water, right? Water, we know from our list of things that are cool about water, is capable of dissolving things and keeping things in solution. So what about we decided at the end of the semester to have a picnic. And I say, meet me down on the lower campus lot, which was closed when I got here, with a sign saying, go to the garage. Got to the garage and it said, garage full, go to lot. I'm parked illegally right now, very illegally. So we go down to the lower campus lot, and there is, I have all this food spread out right on the pavement that people have been parking on all semester, and just no napkins, no towels, nothing, just food right on the pavement. Are you going to eat any of it? Why not? What's on that pavement? What's on there? Oil, transmission fluid, maybe some brake fluid, dry deposition of metals and exhaust, maybe people spit, maybe there's some dog excrement, all sorts of gross things right on that parking lot. The first 2 inches of rain that fall in an urban area are actually categorized as hazardous waste because there's so much stuff, there's so much pollution that's on the land surface, and water is so able to dissolve and keep things in solution that it's really polluted. Floodwaters are highly polluted. They wash all of the stuff off of the land surface and get it into that flood. This was a situation when years ago I taught at Northeastern, and they were building these new dorms, like you guys are building here, building these new dorms, and they excavated the basement, and then there was a flood. There was a rainfall event, and somebody forgot to turn the pump on that pumps the water out of the excavation. So I came back the next day and they started to turn it on, but turns out there was a member of the Department of Environmental Protection there doing random inspections. They took a collection of the water that had just been from the rain the night before, went into the basement excavation, took it, did a quick analysis and said, no, you guys have to bottle this up in 50-gallon drums and have it hauled away as hazardous waste. And there was no hazardous waste in the ground. There was no hazardous waste on the Northeastern campus. It's simply that it went over Huntington Ave, went over parking lots. So because of water's ability to dissolve and keep things in solution, river waters are not only rife with disease, but there's also pollution. And then death, obviously, a lot of people can drown from these rivers. So some, I think, maybe intuitive, maybe others not. But here's the situation. We have a lot of bad things associated with rivers. But in this country, we have, and in this world, we have a lot of people that live next to rivers, which begs the question, why? Why do people live on rivers if you have all this bad stuff? Why don't people stay far away from them? So we start talking about some things. What, can you all yell out some things that are good about living near rivers?
Agricultural benefits.
Excellent. Significant agricultural benefits, both from water supply, thank you, and also from the sediment being there, soil building up, and nutrients. Right, excellent. What else? Yeah, transportation. Free transportation, right? We are pretty much free for drifting down or going on a river up. It's very, very efficient means of transportation, transporting people, transporting goods. So it's good for our economy. What else? Put some of these out. So food, agriculture, fertile soil, you can put those two things. What else? Oh, good. So yeah, there are a lot of places where that's a barrier between two countries. Excellent. So security issues, good. Yeah. I'll just put these out as we talk about them. So excellent, could add that. What else? Can you think of anything else? So a couple of things I always hesitate to talk about last semester, but last semester in Geoscience 1 we talked about Boston water problems. One of the problems of Boston going back through time is that we had a burgeoning population, increasing population, we had no fresh water, right? We're ringed in salt water, and what was happening, those of you from last semester, what was happening to the rivers around here? What were we doing to them? Polluting them. We were discharging raw human sewage into them, right? So yeah, put those, yeah. Raw human sewage into the rivers, so our rivers were all polluted. So with regards to water to drink, we started going, the engineers and Boston planners started going farther and farther, am I doing this right for you? Nope, farther and farther west, and hit upon this river, the Swift River, We actually dammed it up, and now there's a huge reservoir that we use as drinking water. So drinking water is very important, a stable drinking water supply that can be provided by rivers, and even more so if you dam the river. And then waste flushing, back in those days, all over the world, we dumped pollution into the rivers. And it wasn't to be obnoxious, it wasn't to be harmful, it was that we didn't have a lot of bad pollutants, there weren't a lot of people, and so any sort of waste that we had could just go out to the ocean where it just got attenuated. These days we have wastewater treatment plants. We have, from last semester, we looked at wastewater treatment plants. We have a method of taking out a lot of this stuff, but there's still this huge volume of water that needs to be discharged, right? We use a lot of water. Most of us have showered today. You've used water for flushing the toilet, for doing this stuff. The water goes out to a wastewater treatment plant, but now you have huge amounts of water, and nobody wants to drink that, right? No matter how clean you can get it, it's kind of gross. So we discharge that water these days, high volumes of water from municipal and commercial water supply into rivers. So back through time, again, we weren't so good about taking the bad stuff out, but we always had to get rid of this waste. And rivers are very good at waste flushing. Get it out. And rivers, keep saying I'm not going to refer to last semester. Rivers, since they flow so fast, they're actually good at breaking up pollutants and attenuating them, so removing them completely. So waste flushing, energy, right? Hydroelectric power, water wheels back through time. The Charles River Dam was for energy back then. Recreation. So I was actually in a previous life, before I came back to academia, I was a senior hydrologist at an engineering firm, and my first job was the most amazing job ever. I had to go all over the state of Massachusetts and evaluate the safety of the dams. So I'd have to do inspections and then do calculations to see what would happen if it failed, and all of these things, these engineering things. And it was so great because it turns out virtually all the dams in Massachusetts are in state parks. So my job, to be very well paid, was to go out to state parks every day. I brought my puppies with me, and we would hang out at the dam all day, and I'd do calculations. That was 2 years of my life. It was really, really fun. So the point is that we dam a lot for water supply, but also it's kind of more dangerous and more difficult, cumbersome to boat, swim, fish, and do all the things that we like to do for leisure activities on a river, because we're forever drifting downstream. So if you dam up a river, then you have this big water body. It's safer to boat, swim, fish, etc. So we use them for recreation for many, many reasons. Also, the last two are that river valleys are flat. You'll have a better appreciation for this next week when we start talking about the dangers of living on slopes. If you can get a river not to flood, the fact that it's flat, the river floodplain is flat, is wonderful. You never have to worry about a landslide. Flat, and it's difficult also to build a house on a slope. You have to excavate and do all these things, retaining walls and things. So river valleys are flat and easy to build on. And then also the aesthetics, right? That's an important thing too, right? It's beautiful to live next to a river, to see this water going by, looking at the birds, sitting on your back deck, watching the wildlife, etc. So people like to live next to bodies of water. So we have this list of bads, death and destruction. We have this list of goods, aesthetics and water and transportation and fertile soil. So we have to then, we don't have to, we have, through time, and we will continue to, study rivers, study the dynamics of rivers and floods, right? Drainage, basin, drainage area, study them, figure them out, so that we can predict flooding. Why would we want to predict flooding? Well, we want to predict flooding because then we can figure out how close we can get to the edge of the river to optimize on the good list without getting too close and having the bad list hit us. So the question, can we predict flooding? The answer is yes, we can predict flooding. We can predict flooding in many ways. The ways that we're going to do it on Wednesday is by using recurrence intervals. So you have these slides, and I'll go through these a little bit quickly. Recurrence interval is simply a statistical probability. So what you're looking at is about how often, statistically speaking, will this river flood. And the equation is a very simple one. Again, we're getting to the quantitative nature of the class. Very, very simple. statistical tool. Those of you who had statistics, you know N, right? So if you haven't, don't worry. It's very, very simple. So what we're going to do is use the following equation, which is adding 1 to a number and then dividing that number by another number. So very simple. Recurrence interval equation, what these things mean, T is the recurrence interval. Once again, I have put this on quizzes in the past. It's a simple calculation, which you should know how to do it. Recurrence interval, how often a flood occurs, is equal to the number of years of record. So what that means is if you're going out to study a river, how many years of record do you have? Have you gone out to the river for 5 years and studied? Have you gone out to the river for 2 years and studied? And M is the rank. So rank is how big to how small the flood is. So in 1 minute, here's an example. If you're writing this down, there's 2 other columns in it. You go out to the river for 5 years. There's the flood that you measured by doing width, depth, speed. That's in CFS, how much water's there. So you've collected this data for 5 years. The first thing you do, and we're going to do this in class, so I'll refresh your memory Wednesday, is to assign a rank. What's the biggest to the smallest flood? So there's the data again. Biggest flood is 3,000 cubic feet per second. Smallest flood is 2. So 1, 2, 3, 4, 5. Simple. Rank is just the biggest to the smallest flood, and then you're done. You just have to calculate the recurrence interval, which is that equation. Sorry, I put R and T. You can use them interchangeably, my fault. You have 5 years of